Well, welcome everybody to this session of the PAThlestras. Today I have invited Professor Rafael Pelegrini from University of Rio Grande do Sul in Brazil. Professor Rafael is a good friend. He has been collaborating with us with COSMO-SAC. He is an expert on COSMO-SAC. He developed his own code of COSMO-SAC. He shared it with us. And just before this meeting during this week, he sent us a link for those of you that want to test this Cosmo. You can do that. It's a free version of Cosmos, so it has many advantages for those of us that do not have the money to buy the Cosmo RS version. But also he has been using it and coupling it with equations of state, as he will show us today, so that you can apply Cosmo in ranges of pressure that you usually wouldn't dream of. But let me not take more of your time. The point here is listen carefully to what he is going to present. If you find this interesting, you can easily have access to the platforms that he's using, so you can try to apply them to your work in collaboration with him. So without further delay, Rafael, many thanks for being here with us today. We are looking forward to listen to what you have to tell us.
Thank you very much, Professor Coutinho. I'm very glad to be here. Thank you for the introduction. And mainly for the opportunity to talk to such prestigious group and field of very competent and innovative people. As you said, I'm from Rio Grande do Sul, Brazil, very far away from you. So for those of you that have been in Brazil, probably haven't visited this southernmost part where we are. Our university is very close to the Porto Alegre city center. Here's the center. Here is our main campus. We have a nice park around. It's a very old university and very big university. Consisting in many schools. The School of Engineering is 120 years old. We have around 90 undergraduate courses and around 200 graduate programs, more than 30,000 students undergraduate and 10,000 graduate. In chemical engineering, which is my department, we have an intake of 120 undergraduate students per year and around 100 graduate students per year. So what are my topics of interest and how did I end up in thermodynamics? Just so to give you some context. For around 20 years, I've been working in process simulation and optimization. I was the author of ANSO process simulator. Maybe some of you have already heard about it. It has around 20,000 registered users. And also we've been developing this new simulator here called EASY. We read as EASY, including advanced thermodynamics with COSMO-SAC, F-SAC, COSMO-SAC-Phi, predictive Suave-Helishkong, and other advanced mixing rules. And what we realized is you can't simulate or optimize a process if you don't have good thermodynamic models. And we got particularly interested in predictive models, those models that do not depend on parameters, mainly binary interaction parameters, which is something very common. And we started this crusade on how to get every time more powerful, more predictive power in thermodynamic models. That is fascinating to me. But as working in simulation and optimization, you probably heard recently there are several buzzwords like machine learning, artificial intelligence, and stuff like that. So I would like to open with a joke, which I found in the internet. You can check this link if you want. The two guys are talking, and one asks the other, so this is your machine learning system? And the other guy, yep. You pour your data in this big pile of linear algebra and then collect the answers. And the other asks, and what if the answers are wrong? What if they don't look good to you? Well, you just stir that pile of linear algebra until the answers starting looking good. So of course this is a joke, but as every joke has some truth behind it. And with these buzzwords, with machine learning, artificial intelligence, you'll never get new insight. You'll never get insight for something you never measured. And we would like to predict without even having to measure in the future someday. That's the final target. Predict without even having to measure. Of course, we always need to measure to check if your predictions are good, but that would be like a final target. And another figure you've probably seen in several conferences is one similar to this one. We have several time scales and length scales. You can start from isolated molecules down here and use quantum chemistry packages to predict how they behave. And several researchers try to take small steps from one scale to the other. Every time they do that, they need to introduce approximations, and the computer requirements increase. Obviously the final objective is to predict and design and optimize entire processes. That should be the idea. What you probably haven't seen is that, and that's what I find amazing about these models, COSMO for real solvents and COSMO-SAC, is that you start here with quantum chemistry calculations for isolated molecules. This is COSMO alone, for molecules alone. And with COSMO for real solvents or COSMO-SAC, you can make this big jump directly here to your engineering problems. You can compute with COSMO-SAC activity coefficients of substances in mixture at arbitrary temperature and composition of these liquids. One step that's missing here is what about pressure? These COSMO-SAC don't have pressure in its formulation. Pressure is irrelevant. So we can make another jump and try to calculate also fugacity coefficients as a function of temperature, pressure, and phase composition. It can be a liquid, a vapor, a fluid at arbitrary conditions. And that's what we can calculate with COSMO-SAC-Phi, which I will show you today. So first of all, I'm not sure all of you are acquainted or what's your knowledge about COSMO-based models. We have COSMO, which is for molecules alone, and we have COSMO for mixtures, COSMO-RS, and COSMO-SAC, which is for mixtures. So COSMO alone was originally developed for predicting or calculating solvation effects, assuming the solvent around a molecule is as a continuum. So they put the molecule inside a cavity, and around this molecule you have a conductor. For instance, we all know that hydrogen have very low affinity for electrons. So a hydrogen will be partially charged with positive charge, so it will induce on this conductor around negative charges, blue charges, negative. So this is what COSMO alone calculates, these charges around the molecules. This calculation uses sophisticated quantum chemistry packages. They can take a few minutes for a small molecule, but can take hours for a larger molecule, or even days if you have a very large molecule. And this kind of calculation is currently impossible for polymers, for instance. It will take forever. So we calculate these colors, these charges, which we map to colors, and we store them in databases, so we don't need to recalculate that. We have our own database, which is the LVPP Sigma profile database. I invite you to go to your browser. Let me just do that. And look for LVPP Sigma. If you search for that, you reach our repository here. LVPP Sigma is a GitHub repository where you found all the information necessary to use our Sigma profiles and our COSMO-SAC parameterizations. I'll also invite you to enter this website, this GitHub repository, and give us a star. If you click here on this star, is just like in social media. When you give a like or a thumbs up, you can give us a star. This makes our project more popular. We have currently only 19 stargazers here, mostly people from our laboratory, some from other places. You have Virgilio Padua here, maybe you know him. But we would very glad if you could give us a star here in this repository, just starting to make this kind of advertising, let's say. So, and all this is managed by this JCosmo package, which I shared with you with this link. You already have this link. You can download this package. I will just show you how it looks like. Oh, sorry, this one. Here, we can search for molecules. Let's say acetone. We search for it. We can view its surface. Here's acetone. I'm not sure if the delay allows you to see me rotating it, but here's the molecule, here's the surface, the colors, the charges it induces. You see a very nice, usually a very nice smooth and continuous colors, but this is not actually how it's computed. I can show you here the points where you actually have the computation. Just change an option here, and you can see not all the surface is calculated, only some points of it. The small balls shows you the points. You actually have the calculations, which are translated to the colors. So this is for molecules alone, COSMO. For mixtures, for real solvents, we need another step. The basic idea is every molecule consists of several surface patches or surface segments. Let's say we can break this molecule in small pieces like this. We have another segment here, we have another segment here, and all over the molecules. That's the basic idea. So if we put two molecules together, we put two surface contacts. We contact these two surface patches or segments. Before the contact, we had the conductor here and the conductor here surrounding these molecules. When we put these molecules in contact, the conductor is removed and we have no conductor between the molecules here. So we can realize that we keep doing that, putting the molecules in contact, and in such a way that every molecule segment, surface segment, is in contact with another pair of another molecule, we will end up with the real solution where there is no conductor between the molecules. So that's the COSMO for real solvents, where we manage to remove the conductor between the molecule, between surrounding the molecules. So, but every time we have a contact, we have an energy change. And different contacts, when we put together different colors, we have different energies. So we all know that different energies means different probabilities, and contacts with less energies should be more probable. Contacts with higher energy should be less probable. And we see that there are many possible contacts in solution, and we need to actually calculate what are these probabilities to actually compute the mixture behavior. In order to do that, the first step is to translate this three-dimensional information, these colors around the molecules, into a histogram. That's how it's done. Otherwise, we will need molecular dynamics or Monte Carlo to solve these problems. And we don't want to do that. We want to compute mixture behavior without using molecular dynamics and Monte Carlo, and we can do that using simple statistical thermodynamics. That's the idea. So how do we do that? Let's say we have here this red surface segment here. We have another red one here. We map this. Oh, let's say this red is like this red here. So we stack these areas here. Two reds. We have a less intense red here, another here, another here, and we end up with this histogram. For every molecule, we can create this histogram. We call these histograms the sigma profiles, and that's the idea. Using these sigma profiles, which are one profile per molecule, we can actually end up calculating the activity coefficients as long as we compute all the probabilities they have in mixture. And this is very, very interesting because, quoting Prausnitz here, it's always desirable to express properties of a solution in terms of something coming only from pure compound properties. And this is exactly what happens with COSMO-based models. We use the sigma profile, which is a pure component property, and end up calculating the behavior of mixtures. That's the idea. And that can help to explain why some molecules like each other so much, why some dislike, why some molecules seem to not care to be in the mixture or not. We have classical examples here. You probably can't read what's in this figure, but this figure B here is for the mixture chloroform tetrahydrofuran. When we make this mixture, we have a pressure. This is a vapor-liquid equilibrium diagram. We have a pressure much lower than the pressures of the pure compounds, and much lower of what the Raoult's law would say. Let's analyze these compounds here. Acetone is already here. Let's add also tetrahydrofuran. Acetone and tetrahydrofuran. Let's build the surfaces. Oh, sorry, not acetone. It's chloroform and tetrahydrofuran. Let's remove acetone. Chloroform. Let's build the surfaces. Here it is. Tetrahydrofuran and chloroform. So when tetrahydrofuran is pure, this positive induced surface charges have to interact with neutral charge or with positive charge. So tetrahydrofuran molecules, when it's pure, they are always uncomfortable in the pure liquid because we have this mismatch. Same for chloroform. We have this negative induced charge that will have to interact with either negative charge or nearly neutral. So chloroform is also very uncomfortable when pure. And we can see that in a mixture of tetrahydrofuran and chloroform, we'll have a very lower energy when we have this interaction. We know positive with negative, they attract each other, and the final effect is what we see here, with pressures much lower than the pressure, saturation pressure of pure compounds. We can see that also here in the sigma profiles. They are nearly the mirror each other. We have tetrahydrofuran with positive charges, induced positive charge from the oxygen, and chloroform with the induced negative charge from the hydrogen. And so the result is the activity coefficients. Here we have the logarithm of activity coefficients. They would be negative for this mixture. And so we have this negative deviation from Raoult's law. Similarly, for this image on figure D, which is for ethanol and toluene, if we go here and look for ethanol and toluene, you can do that on your computer. You already have this software. We view the surfaces again. Ethanol is here, looks like a puppy. We have positive and negative on the same molecule. They will be a very good electrostatic interaction, but in this case, not only electrostatic, but also hydrogen bond. And toluene will be in the middle of that. So they don't like to be in that mixture. And what we see is that the pressure increases when we mix this mixture. And we can explain all of that with using either the three-dimensional surfaces or the sigma profiles of these molecules. You see toluene around 0, mostly neutral, and we have ethanol with both positive and negative charges. Okay, we can compare vapor-liquid equilibrium here inside J-COSMO. Let's go for the chloroform tetrahydrofuran. Here is the response for COSMO-SAC and also UNIFAC. For this case, we can see that COSMO-SAC produces very good results. This is our own COSMO-SAC implementation. And here UNIFAC, which in this case not as close to the experimental data as COSMO-SAC for this particular case. If we check the other example, which is ethanol and toluene, we can see that COSMO-SAC also predicts the positive deviation, but it's not in perfect agreement with experimental data, while UNIFAC is in perfect agreement in this case. But of course, there are hundreds of parameters being fitted to get these results, while in COSMO-SAC we haven't used any of these data in the model formulation, so these are really predictions. So here we have that examples I just shown you. But how actually these computations are made, how we start from the surfaces, these colors, and end up with activity coefficients. That's very scary for most of us because it's based in statistical thermodynamics. We'll not have time to get in details on this, but we have in our 2-day course what we call a sticky fluid model, where we can easily explain to you how these models actually work. In this sticky fluid, we assume you have several post-it notes or sticky notes, and then they interact only in pairs, like 1 with 2 and 3 with 4, and we can derive all equations in a simple spreadsheet. We can go back if you want. I will skip that for now, and we can understand how COSMO-based models work. We could place sticky notes around every molecule, and we need pairs of contacts, so this sticky note can interact with this one, and then we can derive the model equations. And when we do that, we end up with, for every segment, let's say this is segment M and this is segment N. For every segment, we can calculate what we call the activity coefficient of the segment, and not the activity coefficient of the molecule yet. And we can derive this equation where this activity coefficient of one segment depends on the activity coefficient of all other segments. So this is much more complex than classical models, which are explicit models. You can write it in a simple spreadsheet. This one you need a software to solve, because the activity coefficient of one segment depends on itself, because this list is for all segments, and also the activity coefficient of all other segments. And here is the interaction energy for the contact MN between the segments M and N. So we need to solve this system of equations. So that's not so simple. That's why we have so few implementations of COSMO-based models, because you can come up with that in an afternoon, let's say. And then in order to compute the activity coefficient of a compound, which consists of many segments, you get all the segments that are inside that compound I, all segments of compound I, and you subtract the activity coefficient when they are in a solution from what it would be when they are pure. So you get the activity coefficients. That's the idea. On top of that, you also add the combinatorial contribution using either Flory-Huggins or Staverman-Guggenheim, as in classical models like UNIFAC. But what you end up when you use these equations, recalling that we always have, for every segment, we need another segment in contact, in mixture. They should always be in contact. We realize that should be no empty spaces. So in COSMO-based models, there should be no empty spaces. We shouldn't have these holes here I'm highlighting. We shouldn't have that. This is my fault, because I could not come up with a figure where you can actually see the molecule, but there is no space between them. So just keep in mind, there should be no space between the molecules. So if we reduce the pressure, if we remove this block here, we reduce the pressure, but the molecules should be always in pair contact with the others, so there should be no empty spaces. So we don't take into account pressure. And that's a problem for COSMO-based models. There is no free volume. And the volume of a mixture is always simply the sum of the volume of the molecules. That's the idea. So when you need to take into account pressure, several different groups have been combining equations of state with COSMO models using different approaches. We have some here. This one here is one attempt from our group, where we combined cubic equations of state with COSMO-SAC using a mixing rule. This is what we call the self-consistent mixing rule. We are very proud of that mixing rule since it's consistent. This is self-consistent mixing rule. And more recently, Professor Lin and his group extended our mixing rule to work with COSMO-SAC also. This is the modified self-consistent mixing rule, and they concluded that the self-consistent mixing rule is much better than other mixing rules we have up to now, including Wong-Sandler and modified Huron-Vidal. So that was very nice also, because we are always re-implementing and extending model from others, and this is the first time the same others are extending our models. So that was very, very interesting. And what we came up more recently was a much seamless extension in the past year, where instead of combining COSMO-based models, instead of combining COSMO-based models with equations of state, we made a new equation of state based only on COSMO, based only on COSMO-SAC. The basic idea is, instead of having, even when you have a pure substance, let's say water, now it actually will be a mixture of water molecules and holes. We have holes. And we call this a pseudo mixture. We have water and holes. And what happens if we reduce the pressure, we remove this here, we end up introducing more holes, and we can see the volume increase. That's the basic idea. Sounds very simple, sounds very crude. And the main question is, when the pressure is reduced, how many holes you introduce? Since arbitrary, how many holes you should introduce. And what we were able to show is, if we model the pressure as two contributions, one repulsion and one attraction, we could show that the attraction pressure calculated with COSMO-SAC is simply the chemical potential of the holes divided by the hole volume. That was very interesting, because this is actually a very elegant result, very simple. I like when I see a simple equation, a very small equation, saying that the pressure, attractive pressure, is tied to the chemical potential of the holes. And so that with this, we tie everything together, and we end up, of course, it's not so simple, but we end up being able to calculate fugacity coefficients as a function of temperature, pressure, and composition of any arbitrary mixture using only COSMO-SAC. That's the basic idea, and not combining with an existing equation, but making it an equation. That's the idea. And since COSMO-SAC is able to calculate chemical potentials, it's able to calculate this quantity, and we end up with this equation of state. I will skip some details here for now. One important step is we cannot derive an equation of state by if we not introduce dispersion interactions, which is usually zero in COSMO-SAC implementations. We need to add that dispersion interaction, and we end up having to estimate parameters for this dispersion interaction. That's the idea. And what are the results we see? So here we compare COSMO-SAC-Phi and SR-Chi. When we look for pressures, here are saturation pressures. We can't see a difference between the models, but if we look for liquid volumes here, we can see that the COSMO-SAC-Phi is far superior. Well, we all know that cubic equations of state always generate poor results for volumes, but just as a reference, so you can see how the results are. The same here for some other molecules, longer molecules. We don't have that perfect match anymore, but very good results still. If we go to mixture, start with vapor-liquid equilibrium at low pressures. Here we have some polar compounds, positive deviations at low pressures. COSMO-SAC-Phi here and COSMO-SAC should produce very similar results because pressure is not that important at low pressures. We all know that. And we can see very good results. Just as a reference, we have here SR-Chi results. We know cubic equations of state without binary interaction parameters cannot model polar molecules as we have here. Have mixture with polar molecules. Oh, sorry. Polar molecules. So we always have poor results here for the cubic equation of state. Negative deviations. We also all know that cubic equations of state without binary interaction parameters cannot produce negative deviations. And here we have the COSMO-SAC and COSMO-SAC-Phi results modeling negative deviations. Still at low pressure. What about high pressure? Now we can apply COSMO-SAC-Phi at high pressures as well. And again, we get very good results either for positive deviations as well as negative deviations. What about liquid-liquid equilibrium? As we now can also take into account pressure effects. For instance, here for octane and water, we know they are they have very low mutual solubilities. We have nearly pure water, pure octane. But as we increase the temperature and also the pressure, otherwise we will not have a liquid-liquid equilibrium anymore, we can predict how they become more soluble. And here the same, similar for pentanol and water. And we have here the response for unifac liquid-liquid, nearly insensitive to temperature and of course pressure. This for binary equilibrium. You can apply for ternary or arbitrary number of components. You can apply it to high pressure gas-related systems. Of course, the interest will be when we have polar compound. Let's say we have a gas and water. And here we have results for the Gerg-Water equation of state with temperature dependent binary interaction parameters. They can get this dashed result here. But they need temperature dependent binary interaction parameters. CPA with binary interaction parameters also do a reasonable job. This is of course not a simple system because even with binary interaction parameters, they can't have a perfect agreement with experimental data. And here we have the predictions for COSMO-SAC-Phi, no parameter adjusted to have this. So it's very, very promising. Similar problem with methanol in a gas, in a mixture with gas. Here is the response with CPA plus adjust with a binary interaction parameter. It's a very complex response. We have a reduction and then an increase. And here is the prediction with COSMO-SAC-Phi with absolutely no parameter adjusted for this particular system. And you could ask yourself, well, what's here for me if I don't work with high pressure systems? So I don't care about this. Let me show you another example here. Let's say we will work with, just a second. Let's say we will work with benzene and anthracene. And we are interested in the solid-liquid equilibrium for this mixture of benzene and anthracene, okay? And here are the surfaces. Very similar, right? We can see here the sigma profiles, very similar. Okay, so we would expect that these compounds in mixture behave ideally, that the activity coefficients are very near to zero. They are not zero, there are small numbers negative, because this negative response comes from the combinatorial contribution, because these molecules are different in size and shape. But they are close to zero, right? So if we compare here the response for the solubility of anthracene and benzene, here we have the experimental data. In the dot curve, we have the ideal mixture. So here we have the ideal mixture. We have experimental data, and here we have COSMO-SAC in this dash response. Negative deviation, as we saw in the activity coefficients, but the experimental data shows we have a positive deviation. And this line here, this continuous line here, is the COSMO-SAC-Phi response, because in this case, we can also take into account dispersion and free volume. And this, again, is a prediction. It's not a correlation for this system. We predicted that. We can select another system, for instance, pyrene and benzene. Not so perfect agreement with experimental data, but again, we see a very positive deviation, where COSMO-SAC alone would never predict that, because pyrene and benzene are very similar in terms of their sigma profile. What they are not similar is they have very different free volume. And with COSMO-SAC-Phi, we can also model now free volume differences. And this can be clearly seen here. We have a huge difference between the ideal mixture, the COSMO-SAC, and COSMO-SAC-Phi, and all this is at low pressure. So that's not the high pressure, which is the application for this kind of model. So this is what I plan to show you, and thank you very much for your attention. Here are our contacts, and of course, please, if you have any questions, I'll be very glad to ask and interact with you. Maybe I stop sharing my screen for now.
Rafael, many thanks. It was very enlightening. Your work is very impressive. Let me start with a blunt question. You show us when this works. We have quite some experience with COSMO. We know that COSMO doesn't always work. What is your feeling about COSMO for the type of systems that you have been working, not just these ones that you have been showing us? Is it reliable? Bear in mind that I'm not asking about the extension to high pressures that you are using. I'm asking about the basics of the COSMO. the way it describes the non-ideality at atmospheric pressure, because afterwards what you do is to extend that to high pressure. Is it reliable? Can we trust it? Can we design, would you design a plant based on COSMO?
Do you see me? You see me? You see my
No,
email?
I don't see your image.
Let me turn on. Ah, okay, it was off. Okay, better now. Do you see me now?
Yeah,
okay.
Perfect.
Yeah, I have shown mainly the cases where it works. And of course, we have many cases where it does not. It simply does not work. And when I think about it, we need to realize what are we missing? What's the missing part? And one thing that we lose when we use COSMO-SAC or COSMO-RS is the 3-dimension of molecules that's lost. All molecules are exploded, and every surface segment is available, which is not true. Depending on comfort, we are losing also conformation. We usually choose one, which can depend on the mixture where that molecule is. And we lose the 3-dimensional information. So for molecules like, let's say, benzene, nothing can happen with it. So we are fine. But more flexible molecules, we can lose information, and we can cover a hydrogen bond donor, we can expose a hydrogen bond donor, and that can make a huge difference. Another problem is, speaking of hydrogen bond, the description of hydrogen bond is still too poor. The same for ions. We still have poor description when we go to ions, because those strong interactions can hide part of that molecule, and we assume all is available in that model. So those key points I see as the main limitations and the source of wrong results. I think those are the main sources of when it simply don't work. Also, if you have several different hydrogen bonds on the same system, and a slight difference on one hydrogen bond in respect to the other can produce a completely different result. Like this interaction will actually happen in mixture, while it's completely different in reality, because we have poor hydrogen bond description yet. It's kind of empirical. The hydrogen bond description is still empirical on these models, so we have that problem as well.
Okay, let's open this discussion for the other people. Quite a number of the people that have been attending the lecture, they have some experience, at least with COSMO. Maybe they have some interesting questions or doubts. So please just
go
state
ahead.
your name.
Don't be shy.
We have too many Brazilians attending, and then they are very shy.
Can I do a question, please?
Oh yes, please do say.
Hello, Professor Rafael. It's a pleasure to talk to you again. Congratulations for a nice presentation. So my question is about, because I was trying to optimize in ammonium chlorides, such as choline chloride, using gains as you provide us, the code that you provide us, and but I can't do it, but in creating a new compound. I just can do by separate molecules like choline and after chloride, but not as a new compound. Do you have an idea what could be the problem?
So you're trying to create dimmer, let's say. Yeah, with both the cation and
like
anion.
a new compound.
Mm-hmm. Yeah, that's we have been doing. We have not done that yet with games. I'm really not sure what's the. Probably you need to specify some special option on the game script, because for instance, when you have a cation, a positive net positive charge, you need a special parameter. When you have an anion, you need to specify that, oh, my net charge is not 0. In this case, you'll have a net charge which is 0, but you have both a cation and an anion, so maybe you need to provide some special option. We can take a look for you if you want. You can maybe send us your mol file just as a starting point. Another problem is if you when you create your new molecule, let's say molecule because not a single molecule, and if you accidentally put these atoms too close, the molecule will explode when you try to stabilize the configuration. So you need to be very careful about that, not putting the molecules too close as the starting point, as that can be inconsistent and also generate problems. But we have no experience doing that. We can try to do together maybe.
Okay, thanks. I will try it and I contact you. Thanks.
Okay, thank you. Have you been able to run the program I sent you, or that was too close to the presentation? You have no time? Asking in general.
Hi, can I ask you a question?
Yes, please, Emmanuel.
Thank you very much for the talk. From what I understood from the first part of your talk, you had an approach where you combine COSMO or COSMO-SAC with equations of state, but then you changed to this new approach where you build the equation of state from COSMO. So you completely abandoned that project of coupling with equation of state, and you are only working with this new one, or you are still working with the other?
Thanks for the question. No, we are still working in the previous approach because it actually is much faster. When we combine a cubic equation of state with COSMO, we have very fast results, and we can run simulations for entire processes. When we make this new approach, it's much slower because every time you have a new pressure, you need to discover how many holes do you have. So you add an additional step, making the simulation or the computations in general much slower. So we keep the previous method, but this is more, let's say, a research grade.
But you would say the results are much worse with the cubic equations of state, and
well, depends on the application. Actually, depends. If you need liquid volumes, for instance, the new approach is much better. If you don't care about the liquid volumes, which is usually the case, you're more interested in the vapor and liquid compositions, they are very similar. But this new approach is much more advanced and much more consistent, let's say, because when you combine an equation of state with an activity coefficient model, you also introduce several approximations, and there are some people criticizing that. And with this new approach, we have something more consistent and elegant, but harder to apply in reality because it becomes much slower.
Okay. And is the other approach also in the JCosmo software, or only this new one and normal COSMO-SAC?
On the JCosmo, you will not see COSMO-SAC-Phi, but on that package I sent you, there is the JCosmo/dev, which is for developers, which is also in that package. And on that JCosmo dev, you'll find this new equation of state COSMO-SAC-Phi.
So the normal JCosmo version only has COSMO-SAC and
yeah, and Unifac and other Cosmo parameterizations, but no COSMO-SAC-Phi on that JCosmo.
Okay, thank you.
You're welcome. Thanks for the question.
Other questions? I'm sorry, I lost my connection for a couple of minutes, but I'm back. Is there anyone else that would like to ask questions? Kiki, any curiosity?
No, I'm good, sir.
It would be interesting for you probably to try this version of Cosmo and use it for your purpose at high pressures.
Yeah, sure, because now I'm also comparing the two different Cosmo, the one from Cosmologic and the other one from SCM. So
that would be a good question to Rafael. Rafael, there are plenty of versions of Cosmo. The Cosmo files can be shared between these versions, or the versions tend to rely on Cosmo files that are particular for that version. Can I use a Cosmo file from the Cosmo RS in your COSMO-SAC?
Yeah, this question has two aspects. One is technical, like the file formats are different, so we need to read the files. But this is just technical side. We have support for the TurboMol format on JCosmo. If you go to JCosmo and select on the left side the version that says COSMO-SAC and TurboMol, there's a version for TurboMol. It can read the files from Cosmo RS. The same could be implemented for other file formats. That's just the technical part. But there's another aspect, which is in reality, every COSMO-SAC or Cosmo RS implementation has a set of parameters, which are they call universal parameters, and we need to fine-tune those parameters for those profiles. So you'll get a distorted response if you use files from one package inside of another without tuning these parameters. But it will work. It will not be ideal, but it will work. Or you could just try to tune these parameters, select a dozen of systems and tune those parameters. We tried to do that with TurboMol, with files you provided us a couple of years ago, I think. And we have this TurboMol version, so we can use their files. Probably they cannot use our files because of this technical side of the question.
Sure. And let me ask you another thing, that is, are you already teaching Cosmo to your students? And if yes, at which level?
I teach only to explain positive deviation and negative deviation from Hall's law, not the details, of course, just the qualitative response. I think it's very nice because they can search for the molecules, see the molecules, rotate the molecules. I think they enjoy that, and they tend to understand more why some mixtures have negative deviation or positive deviation at this level.
Yeah, but you are talking about which, it's a graduation level or postgrad, strato, or what?
In both levels, undergraduate and graduate.
All right, that's interesting to know.
So we give them a link, they download, they can see the molecules, but just the basics and qualitative responses.
Anyone else has any other questions to Rafael? I don't think this is the case, Rafael. That's been wonderful to have you sharing with us the wonderful work that you are doing. I can only hope that some of the people here feel really the same enthusiasm that I feel towards your work, and that we will find more ways of join our efforts and do some work together in the near future. Please convey my best regards to your wife and to the people there. It was a pleasure. Thank you very much in my personal name and the name of all team for your time and for being here with us. Thank you.
No, don't mention it. It was a pleasure to me. Thanks again for the opportunity to talk to you. I see that we have many people watching this, so it's always good to try to spread a little bit of what we do. We are always following you, so I also hope someday we can collaborate more, and we are always open to try something new. So please feel free to contact us, you or your students. We are very flexible, and I hope we can correspond to your needs. Thanks again.
Thanks a lot. Have a great weekend, everybody. See you during this week. I'll be back to the office from sometimes during the next week. Maybe we can meet each other. Have a nice weekend, Rafael. Bye, everybody.
You too. Have a great weekend.
Bye.
Bye.